Subscribe to Dr. Khalkar's classroom channel and press the bell icon to get latest updates. Hello everyone, I hope you are doing great. In my previous lecture video, I have discussed about introduction to quantum mechanics, interpretation of wave function and its physical significance. In this video, I will discuss about Schrodinger's time-independent and dependent equations. So let's get started. The content of this lecture video is as follows. I will discuss about why we need Schrodinger's equation, what is a simple form of wave equation, followed by I will discuss about how to obtain Schrodinger's time independent and dependent wave equations. As I have already discussed in my previous lecture video, that Schrödinger developed wave equations for the matter waves that are associated with moving particle. They are basically a linear partial differential equation developed to understand the nature of matter waves in a quantum mechanical system. Schrödinger's equation defines the wave properties of subatomic particles and also predict particle-like behavior. They predict the future behavior of dynamic systems. Therefore, Schrödinger's equations are basically wave equations predicting the probability of events or outcome. Schrödinger's equations predict atomic spectrum of hydrogen, energy levels of Planck's oscillator, non-radiation of electrons in atom, shift in energy levels in strong electric field, etc. Hence, the need of Schrödinger's wave equation is important. Now let's discuss the Schrödinger's wave equation. Consider the wave is propagating forward with velocity v. If p is the origin of the wave, then the particle at point q at a distance x from p will receive the wave x by v seconds later than p did as shown in figure. When a mechanical wave passes through a medium, the medium particle performs a simple harmonic motion, that is SHM, given by an equation y is equal to a into cos of omega t. Let's say this is equation number 1, where capital A is the amplitude of the oscillation and omega is equal to 2 pi nu, where nu is a frequency. This equation is applicable to all individual particles affected by the wave. Hence, its displacement at time t and the distance x from the origin will be y is equal to a into cos of omega in bracket t minus x upon v bracket complete. The wave equation of such wave is d square y by dt square is equal to v square into d square y by dx square, or simply we can write d square psi by dt square is equal to v square into d square y by dx square. Let's say this is equation number 3. As vibration along y direction, we can say y is equal to psi. The solution of equation number 3 can be written as psi is equal to capital A into exponential of minus I in bracket t minus x upon v bracket complete. Let's say this is equation number 4. As we have equation number 4, then let's find out the Schrödinger's time independent wave equation. So differential equation for wave function from above equation number 4. Let a wave function psi is associated with matter waves. The wave function psi depends on the position coordinates, that is x, y, z and time t. The differential equation for matter wave motion with wave function psi and velocity v can be written as diaba square psi by diaba t square is equal to v square in bracket diaba square psi by diaba x square plus dabba square psi by dabba y square plus dabba square psi by dabba z square. Let's say this is equation number 5. So this equation number 5 we can written as dabba square psi by dabba t square is equal to v square into del square psi, where del square is equal to dabba square by dabba x square plus dabba square by dabba y square plus dabba square by dabba z square is known as a Laplacian operator. We have equation number 6, that is dabba square psi by dabba t square is equal to v square del square psi. From that equation we can have differentiation of wave function psi. We can write the wave function psi can be expressed as a function of space x, y, z and time t as psi function of x, y, z and t is equal to psi 0 function of x, y, z into exponential of minus I omega t. Or simply we can write psi is equal to psi 0 exponential of minus I omega t. Let's say this is equation number 7. After differentiating equation number 7, we can write dabba psi by dabba t is equal to psi 0 exponential of minus I omega t into in bracket minus I omega. Again differentiating this equation, we can get dabba square psi by dabba t square is equal to psi 0 exponential of minus I omega t in bracket minus I omega bracket square. Or simply we can write dabba square psi by dabba t square is equal to minus omega square psi 0 exponential of minus I omega t. So therefore from equation number 7 we can write dabba square psi by dabba t square is equal to minus omega square psi, as the value of psi is nothing but, according to the equation number 7, psi 0 exponential of minus I omega t. So let's say this is equation number 8. As we have seen the differentiation of wave function psi in equation number 8, now let's see the differential equation for wave function psi. So from equation number 6 and equation number 8 we can write v square del square psi is equal to minus omega square psi. So dividing by v square we can write del square psi is equal to minus omega square upon v square into psi. Rearranging this equation, we can write del square psi plus omega square upon v square into psi is equal to 0. Now dividing by v is equal to mu lambda and omega is equal to 2 pi nu, we can write this equation del square psi plus in bracket 2 pi nu bracket square divided by nu lambda bracket square into psi is equal to 0. So by simply putting the values of v and omega, we get this equation. Therefore, del square psi plus 4 pi square nu square divided by nu square lambda square into psi is equal to 0. Cancelling the same term, that is nu square, we can write del square psi plus 4 pi square upon lambda square into psi is equal to 0. Let's substituting lambda is equal to h upon mv, that is the de Broglie's wavelength. We can write above equation as del square psi plus 4 pi square divided by h upon mv bracket square into psi is equal to 0. So rearranging this equation, we can write del square psi plus 4 pi square m square v square upon h square into psi is equal to 0. Let's say this is equation number 9. Now let's find out the total energy of the particle. Let the total energy of the particle, that is the capital E, is the sum of kinetic energy and the potential energy. So we can write the equation capital E is equal to kinetic energy plus potential energy. So capital E is equal to half mv square plus capital V. Rearranging this equation, we can write 2 capital E is equal to mu square plus 2 capital V. So therefore mv square is equal to 2 capital E minus 2 capital V. So mv square is equal to 2 in bracket capital E minus capital V bracket complete. Multiplying this by small m, we can write m square v square is equal to twice m in bracket capital E minus capital V. Let's say this is equation number 10. From all above calculations, let's find out the Schrödinger's time independent wave equation. So substituting the value of total energy of the particle, that is capital E, from equation number 10 into the equation number 9, we can write del square psi plus 4 pi square into 2m in bracket capital E minus capital V bracket complete divided by h square into psi is equal to 0. Rearranging this equation, we can write del square psi plus 2m in bracket 4 pi square upon h square bracket complete into in bracket E minus V into psi is equal to 0. Therefore, we can write del square psi plus 2m in bracket E minus V divided by in bracket h upon 2 pi bracket square into psi is equal to 0. As we know that the h bar is equal to h upon 2 pi, which is also known as the reduced Planck's constant. Hence, above equation we can reduce it and can be written as del square psi plus 2m upon h bar square into in bracket E minus V bracket complete into psi is equal to 0. Let's say this is equation number 11. This is known as Schrödinger's time-independent wave equation. The wave function psi and Laplacian operator, that is del square, is equal to dabba square by dabba x square plus dabba square by dabba y square plus dabba square by dabba z square is depends on the space coordinates, that is x, y, z, and does not depend on time. So it is not depend on time, that's why it is called as the Schrödinger's time-independent wave equation. Now let's see the Schrödinger's time-dependent wave equation. Let the wave function psi associated with the matter wave depend on position coordinates, that is x, y, z, and time coordinate small t. The wave function psi in terms of space and time, let's see, the wave function psi can be expressed as a product of two quantities, that is time independent and dependent, as psi of x, y, z and t is equal to psi 0 of x, y, z into exponential of minus I omega t. The term psi 0 x, y, z is depends on the space, and the term exponential of minus I omega t is depend on time. Hence, the equation can be written as psi is equal to psi 0 exponential of minus I omega t. Let's say this is equation number 1. Now let's find out the energy eigenoperator from Schrödinger's time-independent wave equation. So as we know that del square psi plus 2m upon h bar square in bracket capital E minus capital V bracket complete into psi is equal to 0. So therefore, we can write del square psi plus 2m upon h bar square into E psi minus V psi is equal to 0. Therefore, we can write del square psi is equal to minus 2m upon h bar square into in bracket capital E psi minus capital V psi bracket complete. So rearranging this equation, we have del square psi is equal to minus 2 upon h bar square into E psi minus V psi. Let's say this is equation number 2. Multiplying by minus h square upon 2m, we get this equation as minus h square upon 2m into del square psi is equal to in bracket capital E psi minus capital V psi bracket complete. Thus we can write minus h square upon 2m into del square psi plus capital V into psi is equal to capital E into psi. Let's say this is equation number 3, where capital E into psi is known as energy eigenoperator. Therefore, differentiating equation number 2 with respect to time, we can write delta psi by delta t is equal to minus I omega psi 0 into exponential of minus I omega t. As psi is equal to psi 0 exponential of minus I omega t, this is we have already seen, we can write delta psi by delta t is equal to minus I omega psi. Now let's see, capital E is equal to h nu, that is the energy, and omega is equal to 2 pi nu. Therefore, we can write nu is equal to omega upon 2 pi. Hence, energy capital E is equal to h into omega upon 2 pi. Therefore, we can write omega is equal to 2 pi upon h into capital E, that is nothing but capital E upon h upon 2 pi. But h upon 2 pi is nothing but the h bar. Therefore, omega is equal to capital E upon h bar. Let's say this is equation number 4. Now substituting the value of omega in equation number 3, we can write delta psi by delta t is equal to minus I capital E upon h bar into psi, which implies capital E into psi is equal to minus h bar upon small I into delta psi by delta t. But as we know that small I square is nothing but minus 1. Therefore, above equation we can write capital E into psi is equal to small I square upon small I into h bar into delta psi by delta t. Therefore, rearranging equation we can write capital E into psi is equal to small I h bar delta psi by delta t. Let's say this is equation number 5. Substituting equation number 5 in equation number 3, we can write minus h bar square by 2m into del square psi plus capital V into psi is equal to small I into h bar delta psi by delta t. Let's say this is equation number 6. This equation is known as Schrödinger's time-dependent wave equation. The wave function psi depends on the space coordinates, that is x, y, z, and also depend on the time variable t. As it is depend on the time variable t, hence it is called as a Schrödinger's time-dependent wave equation. This is all about Schrödinger's time-independent and dependent wave equations. In my next lecture video, I will discuss about two applications of Schrödinger's equations, that is particle enclosed in infinitely deep potential well, that is the particle in rigid box, and particle in finite potential well, that is particle in non-rigid box, that is qualitative analysis we will see. So don't miss my next lecture video. Thank you. Below this video, in the description, the link of important information related to this video is given. Please go through it. Please like and share this video and subscribe to Dr. Khalkar's classroom channel to get the notifications about my upcoming videos. Thank you.